I did not have much time going through the working of the Cambridge exam style question last meeting. And as promised, here's our video explaining how the concept of equilibrium and the moment of force concepts could be applied in solving the problem. First, let's go through what this diagram tells us. We have a pole here, this one, which has a mass of 10 kilograms, and therefore we can say that the weight uh, of 98.1 Newton is being applied here at the pole's center of gravity. And at the end of this pole, we have a basket which has a mass of 14.0 kilogram, and that the weight should be 137 newtons and is being applied here. The pole's right end is on the wall, as you can see here, and that the pole is positioned like this because of a cable. This cable supports the pole by having its other end here in this part of the wall, 0.9 meters from the part of the wall where the other end is touching. So how much force does the cable exert or the tension in order to get this entire system in equilibrium? So here's the idea. First, we start with the tension, and as you can see here, this tension can be calculated if we know a force here, which can be regarded as a vertical component of the tension that we want. Apart from that, we need an angle. Okay, just for a side trip, remember that in trigonometry, if you have a right triangle with hypotenuse here, say let's call it C, with these other sides to be A and B, then the sine of this angle is equal to this side B divided by the longest side, the hypotenuse. If we rearrange the formula, then we should get this hypotenuse by dividing this side here, opposite relative to the angle by the sine of the angle. Alright, so can we find the angle from the dimensions given? Yes, of course, and since we are interested on the angle only, so we can just take the arctangent of this length divided by this length, which is, in the end, will lead us to this angle value, 26.6 degrees, right? This is the angle here between the cable and the pole. So now, for this other information that we need to find the tension, this vertical force or the component of tension along the y-axis, we can use the principle of lever. If you may recall, it states that the total clockwise moments equals the total anti-clockwise moments when the system is not rotating. From here, we can say that we have anti-clockwise moment using this force here, the weight of the basket, and this distance, plus the weight of the pole times the distance of center of gravity to the pivot point, which is 0.9 meters. We just need to implement the operational definition of moment by multiplying these two quantities since their orientation here is already perpendicular. As per the rotational equilibrium or the principle of moment, this anti-clockwise moment should be cancelled by a clockwise moment. And that the clockwise moment, guys, is provided by this component of tension that is perpendicular to the length where we measured our distance times the 1.8 distance here. Let's place this to the other side of the equal sign like that and do the maths. You can use calculator in physics exam, and that after doing these operations you should get a value of 186 Newton for the vertical component of the tension. Now for the tension, we follow the formula from the side trip, which is this C, or the tension equal to the side C, or the vertical component of tension, divided by the sine of the angle 26.6 degrees. The force exerted by the cable here, therefore, should be 415 newtons. Now for the follow-up questions, we need to find the force here, force R, exerted by the wall on the pole. In this case, we need to consider the other condition of equilibrium, which is on the linear motion. For this to happen, the sum of all forces acting on the object must be zero, like that. Let us just consider the horizontal. There should be a force here that cancels that force R, which is basically coming from the tension in the cable. Recall that we have the vertical component Ty here, and also we should have the horizontal component Tx here. This Tx is the red rightward force opposing the R. And so we should have this horizontal component of tension minus the force R equal to 0, because there is no linear motion and that all force when added yield 0 value. Now let's simplify this. Force R must be equal in magnitude to the Tx, or the component of the tension along the horizontal axis. And because we know T already and the angle here, we can simply calculate the unknown by this: tension multiplied by cosine of the angle, or 415 Newton times cosine of 26.6 degrees, which should give us 371 Newton, the magnitude of force R. Okay, guys, remember the two conditions of equilibrium and how these can be applied in physics problems. Bye.